Welcome to Numerical Calculus and Differential Equations. Today we will start the topic numerical integration. I will start with a motivation about the problem. What is our goal? First, we want to compute the integral of a function f of x in a definite interval a, b. And because of different reasons we will see in a few seconds, I cannot compute this analytically, so I need to do this from a numerical approach using numerical integration. The reason of that could be, for example, that in many applications I don't know the analytic expression of f of x. So, for example, when my data comes from some sensors and I don't have the expression of f of x, but just a bunch of data points. The other case is when I know the expression of f of x, but it's such a complicated function that I cannot compute the integral analytically. We will see an example in a few seconds of each one of these cases. So what we will do in this topic is, this is the main idea, we will try to approximate this integral in such a way that we will use what we learned in the previous topic, curve fitting. The idea is to fit this function f of x with a polynomial and then compute the integral of a polynomial, which is straightforward. Now, there are some functions like this one, Gauss error function, that appear a lot in statistics, for example, that you cannot compute this integral analytically. So the only way we can work with this function is to compute this integral from a numerical point of view. Another case is the mobile robot example we saw in the previous topic. Remember that this robot was sending like an infrared signal, and this was going back here, and then we measured the voltage and we could estimate the distance to the wall. What we were doing is to somehow reconstruct the shape of the room. So we had this x theta and y theta that were giving me the position, the coordinates of the wall, given the angle that I'm using to sense. Yeah. Well, I could use this bunch of data points that I obtain to estimate the area of this room. That could be helpful if, for example, I want to clean the room. Yeah. So if I want to compute this area, I cannot do it using an analytical approach because I don't know the function I want to integrate. I don't have the analytic expression, but I just have a bunch of data points. So the only way I can do that is using numerical integration. Now, what we will do today, I could use this slide as the last slide of this lecture, but I decided to use it from the start. Today, we will see the simple rules to the numerical integration. And in the next lecture, we will see the composite rules, which are used in real problems, but they are based in the simple rules, so it's very important to understand this part. The main idea of simple rules is the following one. I want to estimate this definite integral, and what I'm going to do is to approximate f of x using a polynomial with a very low degree. In particular, degree 0, degree 1, or degree 2 parabola. And then I will compute exactly the integral of the polynomial. Of course, this is going to be an approximation of this integral. So let's see how we do that. For example, with this first case, that is using as an approximation of f a constant polynomial. So here we have in blue, the blue line is f of x. I want to compute the integral of f between a and b. So in fact, I want to compute the area that is here colored in cyan color. Yeah. as I cannot compute this exactly, I decide to approximate f of x using a very simple function, a constant function. Here, for example, we are using this value of the function at this point to decide the height of this rectangle. So this method is called rectangle rule because it approximates the shape of the function in the whole interval just using a rectangle. And I will estimate the area, the Thean area, will be approximated by this shaded area here with lines. Of course, this is not a very good approximation because this is the simple rule, as I said, but we will see how we can improve this using, in the next lecture, composite rules. Now, the rectangle rules has a lot of variance depending on how do I select the height of my rectangle. I could use the value of the function at the left side of the interval, f of a is the height of the rectangle. So the area is this times the length of the interval, b minus a. So in this case, we call this the left rectangle rule. I could use b, the value of the function at point b, and use that as the height of my rectangle. So then the area of the function would be approximated by this fb times b minus a, and that would be called the right rectangle rule. Okay? Now there are many other options. You can use the midpoint value, and at this midpoint value between a and b, use the value of the function there to select the height of the rectangle, and so on. Okay? So this is the idea of the rectangle rule. Now, the other method is called trapezoidal rule. Why? Because it will approximate the shape of the function inside the interval AB by using a trapezoid. So this Thean area is approximated by a trapezoid. And the way we compute this is we will find the polynomial, the degree 1 polynomial that goes through point A, f of A, and B, f of B, compute this line that goes through these 2 points, and then we will compute exactly the integral of this polynomial. The method is called trapezoidal rule because it uses a trapezoid to approximate the area. How can we derive the formula to compute this area? Well, we can, for example, use Lagrange polynomials to compute the polynomial that goes through the data points a, f of a, b, f of b. Here, for example, we are using as data points, a is in this case what we called in the previous lecture data point x0, and b is what we called in the previous lecture x1. So I have 2 data points, and I want to compute the pure interpolating polynomial, so that is going to be a degree 1 polynomial because I have 2 data points, so 1 less is degree 1, and I can use the pure interpolating polynomial from the previous lecture. That would be f of a L0 because point A is x0, yeah, plus fb L1 because L1 is associated to x1, and I can compute in this way who is P1, who is the polynomial that goes through those data points. Now here we just computed the integrals. This is a very easy to follow approach. The only thing here we used is that b minus a, you see, we define h as b minus a. Okay, so the length b minus a is called h. So that's why the final formula, in this final formula, it appears h. Well, this is just b minus a. Okay? You can try to follow these integrals. They are very easy. And at the end, we get this formula to compute the area for the trapezoidal rule. So, as I say in our standard lectures, if you like boxing things, this is something you need to box. Here in the slide is already boxed. Okay. Now, this is an alternative way to compute this same formula. I will skip it. It's a more geometric approach, but it's not useful when the degree of the polynomial is higher. So it is not going to be useful, for example, for Simpson rule. So for Simpson rule, that's the last method we will cover today. The idea is to approximate f of x, the blue line, by a second degree polynomial. Now, if we think in pure interpolation, I need 3 data points if I want to find a parabola. So I'm going to use a, b, which are the points that define the interval where I want to compute the integral, but I need an extra point. Well, we will use xm. xm is the midpoint between a and b. Could it be another point? Yes, but then it's not called Simpson rule. Okay, so that's important. If we are talking about Simpson rule, we will use a, b, and the midpoint between these 2 points. Now, the first thing we need to do is to compute this polynomial, this second degree polynomial. This can be done using pure interpolation Lagrange polynomials that go through these 3 data points, a, xm, and b. This is done in this slide. Now, here, this is what we called x0 in the curve fitting slides. This point, let's say it's x1, and this point is going to be x2. Okay? So using this notation, L0 is the Lagrange polynomial associated to x0, which is a. L1 is associated to x1, which is xm. And L2 is associated to x2, which is point B. Okay, so I hope it makes sense now. So I write here the 3 Lagrange polynomials. Here I'm also using the fact that b minus a is h, so a minus b is minus h. And we will write here, what we have here is in fact the parabola that goes through the 3 data points. Now, if I want to derive the formula for Simpson rule, I need to compute the exact integral of this polynomial. So that's what we would do here, okay? At the end, we have this formula we can see here that where h, recall that h is b minus a, and in this way, we can compute the area that is here shadowed with lines, okay? That would be the approximated value that we will get as an estimation, as an approximated value of the exact solution, which would be the Thian area, okay? This is the code you can use in Maple to compute these integrals exactly. Remember that these are integrals of polynomials, so they are very easy. We can compute them by hand, but here if you want, you have the Maple code. And that is what we covered today, okay? We covered the simple rules to compute from a numerical approach integrals, so from an approximated approach. Here we have the summary of what we got. If we use the rectangle rule, the exact integral is approximated by the value of the base of my rectangle times the height of the rectangle, which could be f of a, f of b, or other variations. the trapezoidal rule, where the exact area is approximated by this formula that we derived. And finally, when using Simpson's rule, the exact integral is approximated using this formula that we derived. Okay? So that's it for today. Stay safe, stay at home, and hopefully I will see you in the next video lecture, or I don't know, maybe presentially. Let's see how all this evolves. Bye bye, see you.